So good morning, or good afternoon, I should say, I'm sorry. So I see we have 74 participants. So I'm gonna give just a few more minutes to let people connect. I know we're on a Friday and I see the number going up a little bit. So I'll give a few more minutes for people to connect and then I'll continue on. Okay, I think we'll get started. So good day. My name is David Kaeli from Northeastern University. This is the second part of my presentation to you on GPUs. Yesterday we talked about the reasons why GPUs have become such a powerful force in the computing frameworks. We talked about some of the technology trends, the differences between CPUs and GPUs. We talked about the GPU architecture, some of the things that had changed over time. We've moved to be, in some sense, more application specific as time has evolved. And we've also looked at how the programming languages, we described CUDA, we described OpenCL, we described HIP and ROCm, and we looked at how they evolved over time. We presented some very introductory examples, particularly of CUDA, and talked about OpenCL in some level of detail. And again, so there's this sort of this tension always between hardware and software, but it's one of the keys and big messages is applications really drive the future of architecture. And so as new applications come out, we have to continually look for improvements in everything from performance, power and energy, as well as reliability and security. So given that you have all these competing needs, today's presentation, we're going to start off by talking about if I'm a researcher and I want to go off and start studying a GPU from its architecture, from the programs that run on the architectures, I really need some tools or frameworks to actually support that. So with that, let's begin. So whenever we're in the process in the field of computer architecture to design the next device, the next microprocessor, GPU, we start with the current generation and we introduce some new architectural design ideas. So I'm showing sort of the design life cycle here. So a new design comes in, we'll actually spend some time considering different architectural ideas. And then we'll go through and do an RTL design to basically describe it at a level that we can start to consider how to do physical design and layout. That physical design then goes through a series of steps in terms of logic and timing verification. So basically takes into consideration the technology that we're going to be manufacturing this device. And then finally, we get to the manufacturing process. And there's a lot of feedback in each of these steps. There's a lot of iteration that occurs. And that iteration is very costly. It takes time. And we would like to have some flexibility and to make that whole process more flexible and more purposeful. The earlier that we actually can provide direction on the next forward path through this cycle, the less work, the sooner we can get to a new device, we can be more quantitative in our analysis of each step. And so we need tools, and we use simulation tools in particular, where instead of waiting till we have the actual device and then going through and evaluating it, early on we want to look at, oh, should we design the cache this way? Should we have more functional units? Should we have 2 processors, more cores? How should we design this? Well, we'd like to have a very flexible as well as a high performance tool so that we can, again, look at design trade-offs. Okay, so with that and so this is commonly done in industry. Prior to my joining academia a number of years ago, I worked at IBM, and I actually started my career in design verification of designing mainframes. And so we went through this cycle, and it was very, a lot of pain. And I was basically involved in the simulation team. And based on I was working on the memory system of the mainframe. It was quite interesting. We could do a lot of high fidelity simulation on the actual physical hardware and identify problems, whether it was correctness, reliability, timing, or just performance early on. What was interesting was being on that simulation team, and with all that knowledge, I actually went through this whole design process and worked with the RTL design team, the physical design team, and after manufacture, the bring up team, where when a particular problem occurred at any one of these levels, our simulation models were used to actually do that verification, problem solving, finding the bugs in the design, whether it's a performance bug, whether it's a timing bug, whether it's a logic bug. So again, the value of these tools cannot be understated. So in terms of for GPU architecture modeling, and I'm going to talk mainly about what I'll consider academic efforts that are available for the general research population, because there are a number of different tools that are within companies that we don't always have privy to. We use execution-driven simulation to evaluate design and design features. So, early on we used trace-based simulation, where we would actually go and generate an execution trace. It could be addresses, it could be instructions, it could have timing information. We would collect it off of a live system and then go off to a software model of the system and feed it in and look at cache hit rates, throughputs, latencies, overall execution time. And so trace-based became a limitation because you're only as fast as how fast you could read a trace. And that trace was stored on, it's because it's large, on secondary storage. So you're running at mechanical speeds back in the day. That motivated the need to go to execution-driven simulation. So here, now I'm basically running an actual program on top of a program that's simulating the architecture. So it's a program running a program. And so you would design the actual microprocessor or GPU to support basically the cores, the memory system, all the supporting logic, and then you would compare it against, you'd have your simulation model, and you compare it against real hardware, and you'd see if the two, were they the same, or was one giving you smaller performance or larger performance, what was going on. And so you would basically go through this design process to design simulators. So execution-driven simulation is currently used in industry, it's used in our research field. For GPUs, there are options out there that are great. GPU Sim is probably the most popular simulator. Models various versions of the NVIDIA GPU architecture. It can run CUDA programs, and also, it provides a richness that is quite attractive. But it models a single GPU, and there have been discussions on some of its fidelity. It is rather slow, so if you want to go into and do architecture simulation, make sure you have your coffee, good coffee maker, so you can wait around and make some coffee. So. Simulations can take hours to days to longer. So also there's been a major effort by the Gem 5 folks to combine their Gem 5 simulation with GPU Sim to have heterogeneous simulation, so a CPU and a GPU. It's a discrete GPU because you're using GPU Sim. And that's been used by a number of groups. There's also work that was initiated actually in Valencia at UPV and transferred to Northeastern in my own group, that was multi-2 sim. And this started as a CPU, a multi-core CPU simulator that we extended to model a variety of AMD and NVIDIA GPUs, and also an APU. So this is basically integrated x86 with some AMD GPU ISA. So there are more, and they tend to be very special purpose and less open. So I mentioned these three. There's a new version of GPU Sim out of Purdue that's quite interesting, and I encourage you to take a look at that as well. Today I'm going to present a different framework that, again, is work out of my own group. And it's not to compare against these others, but we will focus on some of the attributes of simulators, things that you should consider when you select which simulator you're going to use. So I'm going to talk to you about Akita and mGPU Sim. So Akita is basically a framework for developing computer architecture simulators. It's implemented in the Go language. So if you're not familiar with Go, Go is a language developed by Google. It's very C++-like, but it has some very nice inherent features. Features that support efficient simulation, as well as proper software engineering practices that we liked, that we adopt in the Akita model. mGPU Sim is a GPU simulator. Its current version is targeted at the AMD GCN3 instruction set architecture, and it does multi-GPU simulation. So it's basically looking at, as we scale out, how we're actually going to do our simulation. So why do we have Akita and then mGPU Sim? So you can think of mGPU Sim as a instance of Akita. So we have a framework because we like generality. We would like to have an architecture for architecting simulators. And if you come up with a framework that is well software engineered, you can provide for an agile development environment. So very easy to change each part individually. So this is a characteristic that's not true on some of these other simulators. So, so part of the need that we saw was we needed to have a performant simulator, one that was fast enough, particularly as we start to delve into the multi-GPU simulation. Now we basically, most simulators are fairly single-threaded. There may be some multi-threading in them, but they're not designed from the ground up to be multi-threaded. Our frameworks are multi-threaded. We showed you the number of cores on CPUs that's just growing, and we still do things single-threaded. That just seems wrong. So we basically have spent a lot of time and effort of developing simulators architectures that are much more scalable. So let's talk a little bit about design philosophy of simulators. Excuse me. So when you're designing a simulator, one of the things that happens that developers sometimes, I'll say violate. They actually, we have different components in our system. Let's take, for instance, here we have maybe a CPU or GPU core and a cache. And we have some signals between them. We typically would have a way of getting data back and forth. We typically have an address bus and maybe a control bus, whether we're doing reads or writes. So what is magic? We refer to magic is when one component can magically affect a change in another component directly, or has access to that other component directly without following some protocol. So think of this as when I have two software components, and if I have good encapsulation between those two software components, their behavior should be independent. And if I make a change over here, it shouldn't break something over here. Similarly, in simulation, if something occurs over here, it shouldn't affect something over here directly. We have to send a message over to it through a communication, through a protocol, and then a change can occur over here, but not before that. So magic introduces problems with simulation inaccuracy, and it breaks down this nice encapsulation. We really like encapsulation from a software engineering perspective because that builds robust software that can go under change. So I can change this and this should not really be affected by it. So, and again, so encapsulation is key. There are times to use magic if you're doing like functional emulation. You really don't need that level of uh, of you know of interaction or that separation of concerns. And when you want to do some headroom exploration, you may want to you tend to use magic, and again you can relax that particular element. But again, generally, if you're doing simulation, you're building the base simulator, you don't want to go down that path. So again, with another philosophy is simulate with real data. A lot of simulators, basically, when they fetch something, they do a load, they do it to an address, but they don't bring data to, from DRAM to L2 to L1 to the core. They bring a cache line, and what the cache line contains, who knows? So again, you can do that without the data. You can get all these, as I show on the left, all those interactions. But we have a philosophy that it's key to simulate with real data. Things that are data dependent, things that your fidelity of your model will be much higher. Your ability to do validation will be much, much higher, because now you see if your simulator gets the same answer as the hardware. So you can do some nice back-to-back testing. When you go to develop your simulator and perform simulations, you have to drive simulations with a configuration file. So that is that may involve the build or the elements in your simulation. So, cache sizes, number of cores, etc. Maybe other parameters that are part of the configuration. Typically, these are provided in a file, and we believe that having them in a file is a limitation. Tends to be sort of long and has limited flexibility. You make typos. You don't really you can't automate this process, or if you do, you write another program that generates a configuration file. So instead, we basically want to develop a we want to configure this basically in code. So we actually provide a set of tools, and now we can use conditionals, now we can reproduce results, and it's all built in the same language that the simulator is. This has a lot of benefits. Excuse me. Another key concept, and this is one for simulator performance. So on the left here, we show we can have, let's say, 5 different components A through E, and along the x-axis is time. And so during each cycle, we can basically, in cycle-based simulation, we're going to evaluate each one of these components and see if the state changes based on the input, and whatever, if that input change, we're going to update the state. But we do this on every tick. And again, most of the time, the state is not going to change for every component. It may change for the cache. It may change for a core. It may change for a bus. It may change for a memory. But it's not going to change for everything. There is concurrency going on, but again, not everything changes its state. Some things take multiple cycles, and so those components don't change their state necessarily. They move from they are in the middle of a multi-cycle operation, but their actual visible state is not changing. We call this busy ticking. Basically doing the evaluation, checking each cycle, each one of these components. Instead, we look at we see a component. There's we can look at updates of the state. So something happens and we look to see if we have to update the state of the component. Many times we see that, and this may be from a retry of an operation, so we can avoid some of these updates if we're careful about how we're actually updating each component state when we do this. And again, this gets rid of a lot of overhead in our simulation. Because all these updates, all this checking, these are if then else's, you know, your typical checking, and again, very, and this can actually hurt concurrency of the simulation as well. Another concept is hardware is concurrent. In a single cycle, there's a lot of things that occur, state changes that happen in parallel. But still, we simulate and have simulators that are highly sequentialized. We'll go through the first core, then we'll go through the second core, then we'll go through the third core, and update their states. Instead, we believe that you should simulate concurrent digital circuits with a concurrent simulator. Questions come into play where, okay, well, there's a race condition. Who do I evaluate first? Well, that's where we bring in a communication fabric between components that deal with that concurrency. So let's talk about Akita, and Akita, our implementation of a simulator framework. So the name of Akita, it's a Japanese word. If Aki comes from autumn and Ta comes from field. It's actually a location in Japan. Dyson is also a place in Japan, which Dyson is our visualization framework. So just so you know, so Akita is also the name of a dog, very nice dog. So we talked a little bit about cycle-based versus event-based. Let's actually look at what happens. So here, again, time is on the x-axis. We're evaluating 5 different components in our design. Typically, we may have, tens or hundreds of components. But here, we're doing cycle-based simulation. We evaluate state on every cycle. Instead, if we do event-based simulation where we actually look at to see what's been triggered, what has had a change in state, and then evaluate it, we're going to see that the number of things that need to be evaluated are much fewer. And again, so this gets rid of the bit busy ticking. There may be cycles where there's basically no changes, and so we can skip to the next cycle. So each cycle, we're still cycle-based in the sense that on each cycle, we'll look at what events occur and what components were affected. So, and again, we have a lot less work to do here than we do here, and that should be obvious. So again, as we, if we are to evaluate the simulation, and again, let's say that we take as a priority components in the order A through E. So we'll evaluate component A, followed by E. Then we move to the next cycle, we have component D. And so if we did this with a serial engine through an event queue, we're basically doing fewer events, but we're not doing them concurrently. With a parallel engine, each round, we can basically be handling things that occur at the same time. And we have to decide whether these are independent of each other. So we can basically, since they occur concurrently, they basically have a level of independence. And so we can start to, in 7 ticks, basically evaluate the same amount of work here that took quite a few more ticks when we're dealing with them sequentially. So let's talk about our design of components. So a component is an event handler. Components need to be self-sufficient. There's no intercomponent field access, so the core can't go see if the L1 is busy. There's no intercomponent function calls. There's no intercomponent event scheduling. We basically have to go and do some interrogation through a protocol. To affect that protocol, we use connections. Connections connect components. So here I'll connect the core and the L1, and I'll send messages in each direction. We transfer messages, so just like as we would in a well software engineered design, each encapsulated component has an interface, and we provide messages through that interface. That interface is the only publicly visible elements. What's inside is hidden. That's the power of encapsulation. So now I can make changes to my L1. Shouldn't affect my core design. Connections, we have different types of connections. We have direct connections. We have fixed bandwidth connections. We have more complicated ones like PCIe connections that basically for GPUs that have more of a protocol associated with them. So to interact between components and our connections, we basically have ports. So those ports, they are bidirectional, so they can be in either direction. And for each component, it allows you to do peek, retrieve, and send. So again, you have the ability from the connection to go and look in the L1 to see what, and it's only what's publicly visible. And for connections, we can do receives. So basically the ports will provide information back from the connections will receive information from the ports. Dyson is our visualization framework. This is an effort that's ongoing, but as you can see, I can actually get at, so if I want to look at all the level 1 data caches. So here's the L1 data cache 0 through 15. And here I'm seeing in time, I can measure various things that I'm looking at. For instance, here the incoming request rate is in red, and the average request latency is in blue. And so I have a very rich visual interface where I can look at lots of things with a level of concurrency. So I can see what each of the caches are doing. So I can do this through a variety of ways. I can also look at where latency is occurring. So I have time across the x-axis in microseconds. And here's GPU 1's control unit 00. So I look at each, I can do this on a control unit by control unit, compute unit, I'm sorry, compute unit by compute unit basis, and look at and break down the execution to see what's going on internally. So I have a full range of tools available through Dyson for visualization. And Dyson works across different architectures. It works for mGPU sim. It will be available for other simulators in the near future as well. So let's talk about mGPU sim. So basically all the things in orange are our components that we're modeling in a level of detail. We also have the IO MMU and the L1 TLB and L2 TLB that we model as structures. So, a very rich environment here where we are down at the compute unit level, but we can start to build this out. We have the ACE unit, which is done, if you remember from yesterday, basically this is the unit for doing hardware scheduling. So we start with the GPU driver. So we have a user application. It makes API function calls to the driver. And then through the PCI fabric, we talk to, and again, we can model any number of GPUs. Our driver API, it connects with the application, does memory allocation and movement, and kernel launching. So very much like we had for what the host would do. We're not modeling, an x86 or any host per se. There is some work to do that in the future. The command queues, so the driver translates those commands to requests. They get put into queues to the GPU. And again, we only model the driver to GPU communication. We don't model the driver execution latency on the host. So from the driver, we basically send these to the command processor that's going to then send them to the ACE units or do DMA operations or other control signals. So it handles all requests. It handles kernel launching, memory copies, cache flushing, and TLB shootdowns. There's a control port that to send control signals to all the internal components. So again, a very rich component command processor. The ACE units, the Asynchronous Compute Engine. For NVIDIA, this was the hardware scheduler. So this does kernel dispatching. It splits a kernel into work groups, wavefronts, and work items. Or similar would be blocks and taking grids to produce blocks and warps on an NVIDIA device. Dispatches wavefronts to the compute units, one per cycle. And this is usually at a level that's not modeled in most simulators. It's modeled by magic. There's something that schedules it, and it just shows up on the compute units. We're modeling it faithfully as it would be in the hardware. That way we can look at interesting designs for the ACE units. Can a compute unit execute a wavefront? Well, it can. So we basically have sets of rules that allow for when we can actually compute a wavefront. There's 10 wavefronts per wavefront pool and four wavefront pools. We have to make sure there's enough scalar register space, vector register space, enough local data share space. So all of these things we have to ensure before we can actually run that wavefront. We also have to worry about register fragmentation here as well. In terms of the compute unit, we have to do instruction fetching. We can have 256 byte instruction buffer per wavefront, and the oldest across all wavefronts is done for scheduling. In terms of instruction issue, we use round robin over the SIMDs. I think there was a question yesterday on that, and that's how we handle it in on our device, because that's the information we have available from AMD's. Special instructions do not need to be issued. We issue as many as possible with conditions, and those conditions is at most one per wavefront. Cannot issue from wavefronts that have in-flight instructions and cannot use the same execution unit. So again, a set of issue rules that tell us what we can do within the compute unit. So the SIMD execution in the compute unit is pipelined. So so we have 16 execution units. That's a lane, and the latency takes 6 cycles to get through. So a throughput of 1 wavefront every 4 cycles, and then we can execute the next wavefront. And then in terms of the memory hierarchy, we have vector, scalar, and instruction memory. So we have independent L1 caches. For scalar, it's read-only, and it's 1 shared for 4 compute units. And for instruction, there's 1 cache shared by 4 compute units, and it's virtually tagged. So we have to translate after the L1. So for address translation. So we have to model each one of these, and the interconnections to each one of the compute units. We model those as well. So there's a level of detail here that's quite complex. But again, we get, as given that AMD has provided a lot of public documents on how this particular GPU is designed, we're able to actually do that quite faithfully. We also do address translation. Again, another thing that many simulators don't do. So virtual address space, we have a configurable TLB and MMU hierarchy. So for the address translator, we receive requests from, we call it the top, but basically the caches, and basically translate addresses with the TLB MMU, send translated requests to the bottom to cache DRAM, and forward responses back up to the top. The TLB has MSHRs as well, and the MMU and the IOMMU is has a multi-threaded page walker, and again, it's located on the CPU side. For the L1 cache, it's a write-through cache. Again, MSHRs, so missed status holding registers that handle coalescing. It does an in-order return, and it has a pipeline design, as you can see here. So we have to do a level of checking, and there's things that can occur concurrently and those that have to occur sequentially. The L2 cache, so it's a memory side cache. Each unit has part of the address space. A cache line resides in one L2 cache. There's a it's a write-back cache. You flush before a memory copy. It has MSHRs as well. You can coalesce from the L1 caches, and there's a L1 to L2 connection through a crossbar. And again, we can replace this crossbar with another interconnect as well, and very flexible modeling as well. Now, if we want to do multi-GPU, we have to go from one side of from one GPU to the other, and we use RDMA. So the L1 has to check physical addresses locally to the L2 cache and remotely to the RDMA engine. So each GPU has an RDMA engine, and it works as a message switch. So basically handles requests from L1 caches, forward requests to another RDMA, which then fetches data from an L2. So basically you can do a fetch here for data that's located on this GPU, and it'll go RDMA to RDMA from the L2 cache and come back. Okay, so we have to model all those transactions. We have to get all the plumbing correct, and we have to make this all work. We also have page migration, and we model as a baseline first touch base. So where do I access it first? That page comes to that GPU's memory, and we have to flush before we move data. So we have to flush what's going on the where the current page is. It drains ongoing memory transactions, drains the compute unit instruction pipeline, and then issues appropriate TLB shoot downs, invalidating those translations. There's a centralized IOMMU, tracks all page locations, and there's a migration controller for moving page data. So each one of these components has appropriate connections and ports to handle each one of these operations. So that's sort of the architecture of the simulator for MGPU Sim. In terms of workloads, so we have workloads from the AMD SDK, Bitonic Short, Matrix Multi. So each of these, Heteromark is our own workload benchmark. Basically, we have AES, FIR, K-means, and PageRanks, and we have workloads from Polybench, workloads from Shock, and also DNN layers from DNNmark, again, our own workloads. So we have basically 15 that support unified multi-GPU execution, 10 that support discrete multi-GPU execution, and you can run any combination of the benchmarks, and more benchmarks are under development. And we're working with multiple groups of researchers at various universities of developing additional benchmarks for supporting this work. So that's a lot. Let's talk about mGPU sim in terms of simulator accuracy. So when we do accuracy, we're actually comparing against real hardware. Here we're comparing against a AMD R9 Nano GPU. In terms of average simulation error, we're about 5.5%. And this work was done probably 4 or 5 months ago. So I think we're actually even more accurate at this point in time. As you can see, here's the normalized execution time, comparing running various workloads. And you can see we do, execution time, for the ALU, the L1 vector cache. So the ALU, we're seeing some, the R9 Nanos takes a little bit longer. And then on the L2 cache, we're pretty faithful, as well as DRAM. So we think we're doing a pretty good job here. And then we talked about performance. Basically, we can do both emulation and simulation. So emulation, what's different between the two? So emulation basically doesn't do detailed simulation of all the different elements. It basically emulates the execution and gets correct execution of the program. And so we can do this for studying actually the runtime, and we don't get cycles necessarily, but we can look at roughly how long, or look for correctness of the execution through emulation. So we emulate with 2 GPUs, 4 GPUs, again, and cycle-based with 2 GPUs and 4 GPUs. So we're, and then we get when we run this with 4 cores, so basically we get a 3.5 speed up in functional emulation, a 2.5 speed up when doing timing simulation across 4 cores. So we're still working on improving our scalability here, but again, those are really nice, because we're leveraging the multi-core capabilities here. And again, if we move to larger simulation models beyond 2 or 4 GPUs, we'll see more concurrency. We're also 34 times faster than GPU sim. And we're using matrix transpose there as a benchmark for comparing the two. So it's not really, they're modeling a different GPU, we're modeling a different GPU, but for a single GPU simulation, 34 times faster, that's pretty nice. So if you want to read about our simulator, we basically had a paper in ISCA in 2019 on the simulator, mGPU sim, and we also have already have a number of publications where we've done evaluations with mGPU sim, so GPU to GPU RDMA, that appeared in 2019 in IPDPS. If you want to look at concurrent execution, we have a Cal paper in 2019 on PCIe scheduling. In terms of GPU to GPU page migration, we have work that appeared in HPCA 2020, so this year's HPCA, and we just received notice that we have a related paper that on page management and TLB management that's actually going to be in PACT 2020. So, and again, uses this framework. So what's the roadmap going forward? So for our general framework, and this, our framework updates apply to all simulators. We're looking at actually relaxing some of the ordering and having optimistic parallel simulation, so we can break time order and reduce synchronization, and see, we may need to have the ability to roll back, but we can get better scalability. We're also looking at using machine learning to actually, get a balance between accuracy and speed through reinforcement learning. And then we're looking at doing distributed simulation on a cluster. For MGPU sim, we're currently, I believe we have working now concurrent kernel modeling. We have new work on new DRAM technologies, HBM2 and GDDR6. And we have DNN training workloads, multi-GPU and distributed training. Those should be done soon. And we also want to simulate native workloads, connect to OpenCL and HIP libraries. So a really rich framework here being developed. We have also, since we have an architecture for simulators, we have new simulators coming out. So one of my students is working on a new AMD Navi with the RDMA architecture GPU simulator. So that's underway and that's been started. There's an effort going on there. I have a couple of my students working on a RISC-V CPU simulator. That's collaborative work that's being done with Boston University. We have Fuse CPU GPU system modeling that we're doing, and we're doing work on security and reliability modeling in the same framework. And I'll be talking about those two issues later in this presentation, later this afternoon. In terms of researcher and experience, we basically have been taking Dyson and sharing it with the community and actually doing online surveys. So we're getting, we're doing real-time simulation monitoring, we're doing real-time recording, and we're doing, we have the ability to do online data visualization. So some real nice capabilities in Dyson will be coming out. This doesn't get done by one person, it gets done through a community. And here's some of the people, the leads here, Northeastern, of course, but collaborations with BU, UCAM in Spain, and KAIST in Korea have been really key for moving this forward, particularly in dealing with correctness and issues with interconnects and memory technology. AMD has been a great partner. We also have support through University of Pittsburgh, Alibaba, and the Barcelona Supercomputer Center. We again, lots of different collaborators, lots of HiPEAC members here. And as well, if you want to learn more about this, Akita's managed on GitLab. You can go look at it there. And we have a Slack channel as well, and you can join that as well. I just like to recognize the key, the Kita team is led by Yifan's son. Yifan's a PhD student working with me who's about to be an assistant professor at William & Mary in the US. Trinayam Baru, Shidong and Yuhui Bao. These are my PhD students. So with that, I'm gonna take a pause, and we're gonna take a slight break here. I'm gonna take questions right now, and then we'll take a 5-minute break, and then we'll start up with some research in reliability and security. So with that, I see I have a number of questions. So the first one I have, so feel free to post questions in the Q&A. I will do my best to answer them. Just want to check our time. Great, perfect, right on time. So Thomas asks, what would be the advantage of GPU simulator over using a more hardware description language, System C, for instance? That's a very interesting question. Well, System C is a great language. There's a lot of people, I actually have collaborators that we actually do work in System C and try to model GPU architectures within System C. But the level of effort in terms of engineering that's required to make changes to System C, hardware description languages are just a lot harder to work with than high-level languages. Also, some of the performance that I'm talking about may be hard to get with System C. So again, I look at the learning curve. I was skeptical when my student came to me and said, let's go do this in Go. Go, why do we use Go? Go is inherently concurrent. It supports high degrees of encapsulation. It provides great software engineering tools. Even Google will say it's not the most performance language. If you want that, you'll use C or C++. But because of the concurrency, inherent concurrency and other features, as well as some of the simplicity of a reduced language that takes away some of the gotchas in terms of performance that C and C++ can hang you by, we think Go is the right language. We've made this case in a bunch of our papers as well. So, you know, System C, for those of you that are more hardware oriented, you may like to use an HDL, but honestly, for you know, building something that's maintainable and adaptable by the general public, that's going to be a lot harder. So, good question. Igor asks, what about simulating GPUs on FPGAs? Oh, there's something I've tried. It still retains the flexibility in modifying the design, but potentially could run faster since it's more reassemblable running on the actual hardware. What's your view on that? Well, FPGAs are great at accelerating embedded things that you're going to that you want to accelerate, but they're not necessarily good in terms of when you need to go off of the FPGA fabric, and so that limitation of the scalability as you go to multiple FPGAs, because most of these designs will require multiple FPGAs. So yes, you could embed your design in the FPGA. I still go back to the language in terms of adaptability and flexibility and learning curve. That's a barrier to many, particularly computer scientists that maybe don't have that digital design background in there. So I appreciate, you know, System C and FPGAs, but it's a lot harder to go down that path in general for many. Okay, so Giuseppe, did you use a GPU to accelerate the execution of your simulations, or do you plan to do it? If not, do you think it's reasonable to be done or makes sense at all? That's an excellent question, Giuseppe. I've always wanted my students to explore this, but none have. And the argument against it is GPUs really aren't good at making controlled decisions. They're good at processing data. So could we, so how would we simulate architectural features that we need to evaluate their state on a GPU? That's a challenge. That's, in that sense, a CPU is actually very good. The fact that we have multi-core CPUs and they have a large memory system to support us on the CPU. CPUs are really good at doing this kind of work. So I think that's the right platform today. But again, I would love to have someone to work with us on trying to do acceleration on a GPU. I think we'd have to do, I think there's an opportunity to have sort of hybrid simulation where we could run a couple cycles on a real GPU, stop and sort of take a snapshot and do some decisions on the CPU, but then that communication would kill you. So, but again, if there was a more integrated device, this might be a great path. So great question, I appreciate it. Next we have Josie who asks, regarding the ACE simulation, do you even evaluate multiple scheduling policies to reduce the bottleneck in performance? Josie, that's a great question. We can actually model any scheduling policy that's configurable. We actually, I believe right now, only simulate what the current design is supporting, but I think we can relax that and you can actually modify that. So that's a great question. Exactly the reason. And again, you go and change the ACE component, you're not going to be affecting, you know, the compute units, the memory system directly. So great question. Mohammed asks, what are problems with GPU sim? Well, first of all, you know, so there's actually a lot of great work that goes on in GPU sim. There's a new version of it out that is targeting Volta, which I think, and it has some interesting design features. But again, in terms of its ability to be validated and other things, there's still some questions. You know, I think it has some decent fidelity. Again, it's not designed for flexibility in terms of modifiability. And again, it's only looking at CUDA. Now, we believe that our environment is going to actually be able to run a lot of different source languages. And again, it's going to be a lot more flexible. So good question. I wouldn't say that's a problem with GPU sim, maybe some limitations. I would encourage you, there's a paper that was in ISCA this year, 2020, on the new version of GPU sim. So look at the work, it's authored by folks from Purdue, okay? Perry asks, running GPU simulations on multi-core CPUs, are there diminishing returns for running on more cores? AMD have some very high core counts on recent models. Are there many serial aspects in the simulation that limit benefits? That's a great question. That's ongoing work. How much parallelism is inherent? I think we're looking right now through how to break down some of those barriers in serialization by doing more aggressive simulation, so speculative simulation that basically assumes that, you know, there's no dependencies between these components and then rolls back. So, you know, there are limited, you can only go to a certain number of cores. You can't use all the cores. So it's a good question. I think there is more work to be done there. I think we've really only scratched the surface. Kim asks, GraphCore is a British startup which seems to be a competitor to NVIDIA AI application. What are your thoughts around GraphCore? Honestly, I don't know GraphCore, so I have to, but I will look it up and take a look at what GraphCore is working on. If there's an opportunity to work with GraphCore in terms of simulation infrastructure, we would be interested. Okay, so let's see. That was all the questions that were raised online. So with that, I'm going to take a 5-minute break. It's currently 4 after the hour. We'll resume at 10 after the hour. So I'll be right back. Okay, everyone, I think we'll continue on. So next, I think the next discussion we're going to jump into is on reliability. So let's think about reliability. Why do we need reliability on a GPU? Well, first of all, remember that GPUs were designed for graphics and graphics rendering and gaming. And a fault in a game, really, who cares? Maybe a couple pixels are a little different for a particular frame. We probably don't even see this. But now we're using these GPUs for scientific computing, high performance applications, financial applications. The automotive industry is using them, and we did an analysis of some GPUs in autonomous driving and saw that you can miss pedestrians that are in the road, all kinds of things that are rather safety critical. So reliability is a major issue, and it's very much an afterthought on the GPU. So how do we go about analyzing GPU reliability? So why do we have problems with and again, some of the things I'm going to say here are issues in the reliability of CPUs as well. I've worked on reliability actually, way back in as early as 78. I was working on reliability of memories on mainframes, injecting soft errors off of radiation into memory chips, and looking at how to design them in a way that basically could be more fault tolerant. So this has been, for the high performance computing community, it's been a major issue. Why? Because in high performance computing, applications many times require thousands and thousands of cores, hundreds of GPUs, and if one of those devices gets a wrong answer, the integrity of the whole computation is in question. One of the barriers to having exascale has been identified is the reliability of particularly GPUs. CPUs tend to be a lot more fault tolerant. We've seen fault tolerance built into many high performance machines. Back in the day when I worked on reliability on mainframes, we would design a mainframe and it would have its own a separate processor that all it did was go and check the mainframe and check for its reliability. And again, that was very powerful. But then we had IBM was so focused on reliability, they had a second. These are smaller mainframes that would check the checking mainframe. So they would check each other, and then they would check the mainframe. So reliability has been with us for many, many decades, and customers are actually willing to pay for it. So why does it occur? Well, devices basically are storing charges in both in the data path and memories. High energy particles from radiation from the atmosphere, as well as from semiconductor materials, can generate charges. And basically, we can take, for instance, here we have a 1 stored in this device, and that can get, bit can flip. So single bits and single cells are usually the target. though we have seen work that shows that multiple bits are also susceptible as well, and we've done some studies of those as well. So these are transient faults. They're a top challenge for exascale systems. If you look at this, there's a number of HPC systems basically experience a fault every few tens of hours, so this is not good. This is actually off of real data taken from some of the high performance computer centers in the US. And so, you know, it's crucial that we have some way of understanding how faults affect GPU systems. So, you know, basically these hardware, we need some hardware mitigation techniques to reduce the penalties in performance, power, and area. So, you know, they're expensive. We can have redundancy. So, you know, the typical way to provide resilience to these type of soft errors is to duplicate portions of the hardware. You can duplicate, or you can duplicate things in time. So you could use the multi-threaded capability and run 2 threads, and if one thread gets hit, or maybe you run 3 threads and you do triple modular redundancy where you check the result of all 3 and you trust the result of 2 of them. So there's ways of doing this, but they all cost performance, power, and area, as well as time. And so there's been a number of studies that have looked at this. So, whoops, I'm sorry, going the wrong direction. There we go. So how can we actually estimate reliability for GPUs? So the 2 standard methods, the ACE methodology that was developed by Subbu Mukherjee in his work while he was at IBM, and he worked with a large number of people on this. There was further work by myself, Vilas Sridharan, who's at AMD. Basically looked at ACE analysis on different devices, and there's also the ability to, so basically this takes, think of a simulation of a device. Let's take a GPU, and what we say is if any bit in the simulation in the physical device state changed, how likely is it to actually propagate to a visible program output? Will we see a change in the result of the computation? This is how ACE analysis works. It does a bit of an over computation on you know, how susceptible you are to faults. Fault injection is another technique where I take a live system and I say, oh, let's change that bit. Let's change that bit. Back in the day when I was working at IBM on mainframes, I built something called a bug box that basically could go off and flip bits at various points in time based on the state of the system, and injects very detailed faults and see how the system reacted. So fault injection you can do on live systems, you can do it in simulation, but it requires statistical significance to actually have enough injections to get confidence in your results. So again, ACE analysis, it's you know, typically implemented in simulation, and its accuracy is as good as the simulator, but does comprehensive reliability evaluation, and you get a result in a single simulation run, but it does an overestimation of application vulnerability. The implementation is extremely time consuming, as I can vouch for through the thesis of Vilas Sridharan, and requires a model of the architecture. Fault injection, basically flipping a bit in a structure under evaluation and then observing the results. You repeat that a statistically significant number of times, and so it's very straightforward, it's very accurate, but it takes thousands of simulation runs and very, very, very time consuming. So for a GPU, for fault injection, we have a tool named Sassify, which is built off of SASE. SASE is a binary instrumentation system, very similar in nature to what PIN is. And I recognize that there's even a more current version of SASE that NVIDIA has now. But the Sassify tool was designed, it works with the Kepler frame, GPUs, basically allows you to run directly on real GPUs and inject bit faults in the actual simulation state. So there's, using Sassify, there's 3 steps that to use it for fault injection studies. You basically have to do profiling. You have to find the potential GPU injection sites. You want to inject into live state of the GPU. If you inject in state that's not live, you're really not going to see anything happen. So if you go off and change a register that's not being used, or if you change a memory address that's never referenced, this is not very interesting. So you get a possible injection sites. The second step is you then take those injection sites and you inject a statistically significant number of injections, 1 per run. And then, so you take it from this fault list, you select them, and then then you do the fault injection and check the result. And so this can take a significant amount of time, but again, you'd like to be able to optimize how many of these that you actually need to do. So again, if you look at faults, so you're looking at, we're basically modeling things at microarchitecture and architecture levels. We're injecting single bit faults. The particular study here that we're doing, we're injecting faults and destination values of dynamic instructions. So register and memory contents. The fault injection is at the GPU binary level in the SAS. So we actually change the state and see if it propagates out to an application output. So we have, ground truth, which is the program without faults, and then we can see what happens when we inject those faults. We have 3 possible fault injection outcomes, those being whether the fault is masked. So it was injected into a live program state, but based on maybe where we're doing that operand with all ones or ORing it with all ones, and so it didn't matter whether that bit was 1 or 0, you're still going to get all ones on the output. So in that sense, the fault is masked. You can have a silent data corruption, which is actually the worst, which is we injected into the live state and the output of the program changed, but we didn't detect it. Or you can have a DUE. So this is an uncorrectable error that basically gets injected and it crashes the system, or we had just some sort of non-zero exit of the program. So it was detected by whatever checking, either hardware or software that's provided within the program. And so we actually see that we're able to capture those. So, in terms of doing the, how reliable a particular system is, we wanted to see how input data to a GPU program and its execution parameters influence the program performance as well as GPU reliability. So, so we have a number of inputs and configuration parameters to a GPU program. We have the inherent reliability characteristics. This basically, then we see how with different inputs and different configurations, how does reliability change? Is reliability a function of program inputs and configurations of the GPU? So things we've studied, we've changed the input sizes, the size of the input programs. We've changed the input values, the actual, will all ones versus all zeros change, the susceptibility of programs. We've done program-specific biased inputs for reliability. So we've looked at various things in terms of how much simulation do we need to do. In the end, we're trying to limit the amount of simulation while still having high confidence in our estimates. So here we change the input sizes. So we look at 3 workloads, Gaussian, K-means, and NW, which basically actually we go across 6 different workloads, but for those we saw the largest changes. So we're basically here we're changing the size of the programs here. Each one has a different program type. You know, Gaussian is a matrix, Hotspot's a matrix, Lava MD is a matrix. The rest are vector. So and again, we see how this profile changes in terms of mass, SDCs and DUEs, and you know, so here we see a shift. You know, Gaussian seems to be very sensitive in terms of the profile, and again, all we're doing is changing the size of the input. We're not necessarily changing the data values or the profile of the data values. We change the data values to programs, so we can just randomly change in the input values. They don't really significantly change, as you can see, for each of these 6 applications. So the profile shifts maybe a little bit, but it really, so the input values were generated through the program's old input generator. So again, don't seem to be highly susceptible. But if we used biased inputs and configurations, so we basically look at each one of the applications. So breadth first search, basically if we use higher edge density, the average number of edges per node is 200 versus 8. This is what we call our biased input description. So for Gaussian, the input values are chosen so the system accepts infinitely many solutions. Hotspot is a simulator that basically where we change to increase the number of iterations of the kernel. And K-means clustering, the maximum number of clusters was changed from 50 instead of 5. So it's going to run longer and do some different paths through the execution. And we looked at, so we see that for standard and bias, we see a more significant shift. Here we see significant change in terms of the SDCs. So with biased, fewer SDCs, more masked, and about the same DUEs. Again, we see some shifts in when we use these biased inputs. So if we look at purposeful changes in the program inputs and configurations, we'll see some significant differences in terms of the profile. So just to summarize, you know, if you're often working on GPU reliability in your work, here are some things that you should consider. You have to understand the sensitivity of your experiments in terms of different types of input sizes and values. And we saw that you know, the input sizes and bias can change that profile of your reliability. And so when you're actually doing this work, you really should be using multiple inputs and different parameters for your simulation to actually get a more representative sample. Otherwise, you may be misled that you're only studying some limited behavior of the application in terms of its reliability. Okay, so next I'm going to talk a little bit about security. And in this sense, we're going to talk about GPU security and its resilience to side channel attacks. So I've been working on side channels on CPUs and GPUs probably for the last 5 years. And GPUs more recently, very detailed study. A lot of this work is with my colleague, Yancy Fei at Northeastern, and our combined student groups. So GPU security, you know, we're actually starting to move more and more workload off of the CPU and onto the GPU. We already know the CPU has holes. We've had Spectre meltdown, all kinds of different classes of attacks. And so we need to consider, encryption and decryption could benefit greatly. It actually is AES is a benchmark in a lot of the suites for GPU performance. And there's a lot of implementations in terms of how we can offload and leverage the GPU for encryption to be an accelerator for supporting encryption, decryption dynamically on a particular platform. But, you know, once again, we got these graphics processors. They were designed for primarily graphics and, you know, 3D rendering. And so now a lot of thought was put into whether they're vulnerable to attacks that can leverage their physical implementation. So, you know, we need to think about some countermeasures that can actually hide, you know, can protect the hardware and software against attacks while not compromising the performance of these systems and their scalability. So typically the idea with a side channel attack is you're going to, you can have time, power, or electromagnetic emanation. So anything that can, based on what's executing on the GPU, generate a signature. That signature can be in the form of time delay, can be in the form of power usage, can be in the form of an electromagnetic signal that's emanating from a particular you know, device or bus. In this work, we're basically going to focus on, we've done work in all three of these. We're going to focus on timing channels. Because timing channels, you know, has some relationship to performance. So we can actually build on some of the discussion we've had already in this presentation. And we're going to look at particularly memory timing. While there's other types of timing and attacks that are out there, memory and the memory hierarchy has been attacked. And this has been common on CPUs and GPUs. We're going to look at it on how a GPU can be attacked. So again, what the typical approach is, the attacker basically is going to run a watch through, it can be sitting on, say, the CPU and seeing how long a kernel takes to run. And based on doing some timing measurements, will generate traces. Those traces, so maybe I'm doing, you know, millions of encryptions, I'm going to capture samples, and until I have enough samples that give me statistical significance to, I'm going to find some correlation in terms of values. If I know, for instance, what the ciphertext is, and I know something about the encryption scheme that's being performed, I can basically recover the encryption keys. So the encryption keys are important because that will allow me to decipher and decrypt the encrypted text. So, and what happens is that those timing traces are a function of the memory access patterns that are generated. So for instance, if I store my keys in a table and I access that table in a certain way, I can recover the pattern of accesses to that table through timing traces. And that's what I'm trying to do here. So what's key is, so I have timing traces and the memory access patterns. How can I actually perturb some of those memory access patterns to decorrelate the parameters and protect the key? So you still allow the attacker to collect traces, but because of you introduce some non-uniformity in the memory access patterns, you're decorrelating the memory access pattern and the actual keys that are stored in memory. So you know, so the scenario is threads within a warp are going to send a memory request. One of the things that happens on a GPU, if there's good spatial locality, the coalescing unit on the GPU will collapse multiple requests within a range to a single cache line. The result is a cache hit or a miss. In the case of a miss, a request occupies one entry. in a set of MSHRs until the miss is serviced by the L2. So coalescing attacks, we actually were the first to describe a coalescing attack on the coalescing unit on the GPU. So that's this paper that appeared in HPCA 2016. We had showed how we could recover AES encryption keys. So we attacked the last round of AES, and we use the last round because it's a simpler step in the AES algorithm that allows us to, and we were looking at a T-table implementation, which stores that table in memory, and we're able to basically recover, we record all the possible key values. We have 256 different key values for that key, and we basically evaluate the correlation, and we do the absolute value of the correlation to get to the strongest signal, and we see that we have a very clear value that we can recover the key. So we've been able to demonstrate this. We calculate the number of unique cache lines based on, for each one of the, if we guess a key, and then we calculate the correlation between that execution time and that value. So, so this has been demonstrated to be very leaky. There's a lot of other classes of attacks, prime and probe, a variety of others that can be, and we also have demonstrated banking attacks on the cache in further work. Here we have a test kernel with 32 parallel threads. One of the things that's challenging about a GPU is there's a high degree of concurrency. And so getting timing information with all this concurrency, it's a bit of a noisy channel. So you're going to actually, so you have 32 parallel threads where there's 32 loads with n unique cache lines. And so the coalescing unit is going to, based on the where we're accessing within the cache line, coalesce those into a fixed number of accesses. That will determine the amount of time that they take. So here, if we change the width of the coalescing unit, we can see that we get different timings. A narrower width of 32 gives us about, this is in GPU cycles, a little over 500, where if we go wider, we can actually, with a wider coalescing unit, we can actually reduce the number of unique, or the number of unique references that are made and reduce the number of total cycles. What we're trying to do here, if you can modify how coalescing is done, then you can actually hide this timing channel that's available to the attacker. Well, we've studied this extensively, and there's been other groups. The BCOL work out of William and Mary is a particular one that basically showed you could modify the width, as we're showing here, and actually get, you can hide, make it tougher for the attacker to actually recover the encryption keys. To do what you're trying to do is you're trying to the signal to noise ratio is what you're trying to, you want to reduce the signal to noise ratio, and to do that, what you want to do is to introduce some randomness into the timing channel. So changing the coalescing unit width dynamically could do this, but the BCOL approach showed that that actually hurts performance significantly. So what we've done is we actually take, if you look at randomizing the width of the coalescing unit, and here's the signal to noise ratio, you can see with different widths we get different signal to noise ratios. And again, if we use a fixed random width versus changing that dynamically, we can really get much lower signal to noise ratio. So, and again, all we're doing is across each of the blocks having different coalescing widths. We've actually looked at a a design where we have a hierarchical MSHR. We've actually implemented this in simulation where we're doing this on a Kepler K40. And we have a set of 32 MSHRs for tracking the L1 misses. And so basically we're looking at how many different misses are generated to generate redundant L2 requests. So we introduce a second level MSHR that can unify all the inter SM requests to avoid redundant requests to L2. So this both improves performance, but also introduces obfuscation in the timing channel. So we actually have an architectural feature that we've been able to implement and provide for obfuscation that improves performance and lowers actually the timing leakage. We also have looked at a technique where we actually rotate the T-table. So you actually rotate entries over time to prevent the attacker from detecting a rotation pattern. And so you can always recover you can always decrypt and encrypt accurately based on the rotation. But we basically have developed a T-table rotation in memory. So think of it as a hash. So we evaluate these in our simulation infrastructure, comparing security and performance. So we'd like to improve performance where greater than 1 is basically gives us, this is a good thing. We basically looked at how we can do both a fixed width coalescing unit, a dynamic width, and then with hierarchical MSHRs, we actually get a performance boost, so almost a fairly significant one, almost 7% performance boost. Then in terms of the table relocations, rotating those columns, we actually look at how we reduce the signal to noise. And so the number of samples that are required, in terms of a factor, we basically see that if we reorganize every 1,000 relocations, we can get a decent factor in terms of the number of samples that are required to recover, and this is relative to the baseline. So this is a factor, a normalized factor based on the number of samples that are necessary to recover the key, all 32 keys. So, I'm sorry, 16 keys. So, and again, we've done this and measure performance. So here, this is costly. So maybe a good trade-off here is this takes almost 70 times more samples. And again, so we're trading off how we do obfuscation for performance. So our observations here are, GPUs are very vulnerable to timing channels. The memory system, this particular work, by the way, is going to appear in Host 2020. And the citation is below, so I encourage you to take a look at that. Randomizing the width of the coalescing unit dynamically introduces noise, which is great. A second level of MSHRs can further obfuscate the timing channel, and adding software-based methods to do table rotation gives you further benefits. And again, we can increase the amount of time to require the number of traces by 55,000x over the baseline. So generally, you need tens of thousands or hundreds of thousands of traces. So we're talking about, if this is 100,000 and this is 5,500 more x, so we're talking, 5 billion. So this makes the actual attack, so robust to attacks. At that point, the effort to do that is just too much work, and the time to recover the attack, you can change your keys in that time easily. So with that, I'm going to shift to the final portion of this talk, which is what I feel are some exciting directions for GPU research. I covered some of these when I was given a invited talk at HPCA, and I presented some of these there, and I'm just repeating them here because for this audience, not everybody gets the HPCA, and maybe they didn't see that particular, because HPCA was in person versus being online. So I thought I'd cover them here because they're all about GPU research. So GPU memory coherency. This is an area that my team is currently looking at and doing a lot of work. Current multi-GPU systems support memcopy and GPU direct RDMA, as we saw in our simulation, but the approaches basically impact how much memory capacity we have, and we get NUMA effects, non-uniform memory access effects. So basically, remote accesses are very slow, and they require the programmer to identify data races. All these are bad things. There was some nice work that was presented in HPCA 2013 on cache coherence for GPU architectures. There's also been work on coherence architectures between CPU and GPU for like an APU design. The UMH work that was done by our own group that was presented in TACO in 2016. And there's been more recent stuff on time tagging that was basically timestamp-based coherence for GPUs in HPCA 2018. All of these seem like interesting paths. There's also been some other work on MCM GPUs and beyond the socket work. So pointing you to some work looking at how we do memory coherency. This can really help us in terms of multi-GPU. So additional directions, whoops, sorry. I guess I have a duplicate slide there. In terms of additional directions, memory consistency, rate buffering. So basically, read-write partitioning and GPU coherence were done in the quick release work that appeared in HPCA 2014. I think these are all interesting approaches. Formal analysis of NVIDIA's memory consistency model by the group, this is in ASPLUS 2019, that looked at a formal analysis of NVIDIA's PTX memory consistency model done by Dan Lustig, who's at NVIDIA. It came out of Margaret Martinosi's group, who does a lot of similar work. And then the hierarchical multi-GPU HGM coherence, again, looking at cache coherence protocols across multi-GPU systems, was presented at HPCA this year. The problem with this work is, it relies on memory scoping and restricts coherence to programmer-defined regions. Again, or it may introduce some performance. And again, we don't want to add more burden on the programmer to maintain all this coherence and performance. So we need better solutions. Some work that I think is promising. So our work on MGPU sim. So if you go to our ISCA 2019 paper, you can read about COMA and ESI page-based management and coherence. So doing memory management at a page level. Also our page splitting work that was also presented there, where we basically could split pages. And then our most recent work at HPCA 2020 on Griffin that did efficient page migration in multi-GPU systems. Also, I mentioned before, there's work coming out in PACT, again on TLB management as well. So to summarize, I think we've basically talked a lot about GPUs from very different perspectives. We're going to see, GPUs are going to continue to be the accelerator of choice for more and more applications. So applications are what drive the need for new architectures. And so whether it's improving the single GPU to be able to do tensors better, whatever it is, be able to do graphs better, there's a lot of room for future work on GPU microarchitecture. GPU programming languages will continue to evolve. We're seeing work in HIP and ROCm, languages and runtimes for portability and for scalability. We're seeing new, I think we're going to see more and more work in high quality simulation tools. I invite you to join the Akita team if you're if you're interested. We continually are increasing the number of groups internationally that are working with us. We are a very international team ourselves already. We've seen that GPUs are susceptible to reliability and security concerns. So I think the future for GPU research is quite bright, and I encourage you to join. With that, I'm going to finish and take questions. So I'll leave up my last slide here and go to questions that you might have. I guess I have to break out of the, here we go. So questions from the audience. So Isil asks, due to rapid changes in the microarchitecture and low-level tools needed to be replaced for new GPU versions very often, as you mentioned, for fault injection tools, Sassify 2017 versus NVBit 2019. What is your advice for smaller research groups? How can it be feasible to deal with those fast transitions? That's an excellent question. It's a real challenge to stay nimble and work off the latest GPU architectures. I will say for whether it's reliability, whether it's performance analysis, working with a recent architecture with recent programming stacks is critical. And again, there's larger community efforts. We think that the Akita effort is an ongoing effort that's going to continue to, we're already working on the current generation of AMD GPUs in this framework. Also, we're working on a RISC-V implementation as well. So we continue to build this, but only through collaboration with others. You're right, small groups. I don't have a huge group, but I have a large group. I don't think we can do this alone. We need to work as a community. All of our work is open source, and it's all done by community work. So great question. I think it's be part of a community. Isil asks, is the ACE PBF analysis valid for GPU execution? So I have not seen work done on ACE analysis for GPUs necessarily. ACE is challenging in the sense that with ACE analysis, you may be overestimating the vulnerability of because you're basically looking at, if something happens here, will it propagate? So you're looking at diffuse chains, and you're not necessarily have all the dynamic execution available to you. So that's a good question. It's a hard question to ask, and again, it doesn't always get at all the masking that's actually done in the execution. So I'll say that the ACE PBF analysis is a great area for some further research. We've had students look at that, and there's people at AMD that are working on that as well. So I think there's work to be done there. And then Lou, hello Lou, asks, since simulation is time consuming, what about using instrumentation tools such as NVBit to inject faults? Also, which microarchitectures are targeted to inject faults? So right now, so NVBit is I think the new fault injection tool set that's, or more recent tool set that's, that works. And I have to be honest, I don't know all the details of it. It was brought up, I think someone brought it up yesterday during a discussion. And so I do need to look at the current support for NVBit, which architectures but could we, so which microarchitectures are targeted for in the injection of faults? I'd have to take that offline. I suspect you can find that on their website, but good question. Jiwan asks, this is not much of a technical question, but it seems like your work on a wide variety of problems related to GPUs. I guess the performance perspective and students' perspective would differ. But how do you decide to jump on problems? I'm sure so many problems seem interesting, but there is a finite amount of time and resources. That's an excellent question. I look for interesting questions by talking to industry. I ask what their problems are. I try to understand, what their challenges are, and then I actually and many of the problems we work on, my students actually go to industry and spend time there working during internships and co-ops. And so they're informed on what the companies care about. Those relationships are key to do relevant research. Understanding, and it's not always that industry has all the answers, and there's a lot of things they'd like to do but don't have time. That's what we're really good at in academia. So it's a great question. I like your question very much. Thomas asks, how can GPUs be improved in order to outperform SIMD CPUs, especially in optical flow computing? That's an interesting question. To more outperform, I guess. So, because AVX is you can do a lot with AVX. We're currently looking at how to do jitters on AVX and how that compares to GPUs. So I think GPUs can, things that GPUs have to do some things more aggressively. I think one area is sparsity. I know my own group has looked at sparsity in the data path and looked at how to adapt when there is sparsity dynamically within the data path to reduce the memory bottlenecks. That's harder to do on a CPU. And again, so there's some opportunities to do that in the GPU system. So, but optical flow computing, that's a streaming application. That's an interesting question. I'd have to think a little bit more about that, but happy to have a discussion sometime. Perry asks if these tools are working in open source. Yes. And does that relate when simulating architectures from industry partners with IP interests? So it is challenging to get all the details of an architecture. NVIDIA tends to be more closed. AMD tends to be much more open. I will say even, utilizing the, Sassify, that was really hard for us to actually work with and actually manipulate. So interesting question, yes. Is there scope for culture change from hardware design firms to open their designs? Yes, I think RISC-V is actually going in that direction. I applaud that effort, and that's why I'm involved in some degree. But again, it's always going to be that industry has to protect their secrets. But I wish that industry could at least engage academia more. I think it would, again, further advance the field. So just my 10 cents. Samdip asks, while working on embedded GPUs or GPUs in low power multiprocessor system on a chip, do you see the challenges in such GPUs different from the general purpose ones? What is your opinion on that? Well, you still have performance issues. You have power is going to play a bigger role, so that's an interesting trade-off. And actually, for MGPU sim, we are looking at power models and integration of those. I do see that the CPU for integrated SoC devices, the CPU has to play a bigger role. So having an APU configuration where you can offload and flexibly move things back and forth between CPU and GPU, because the CPU there is probably going to be as beefy in some ways as the GPU. So it's going to be, because the GPU doesn't have as many SMs or compute units in APU class devices. So I think there's going to be a lot more need to use both CPU and GPU concurrently. And that opens up some very new areas. So I think that's a great question. David asks, what do you think that the graphics functions rendering will be relevant in future GPUs? Or do you see a shift toward more general purpose parallel architectures? That's a great question. So there's still going to be graphics GPUs. That's the main business for NVIDIA. AMD GPUs, they're in all the PlayStations and all the gaming consoles. Those are going to continue. Those are going to continue independently of, I think, what we're seeing is, in the V100, A100 class of systems, where the focus is on mixed precision and on doing tensors, and how do you build more tensors. Google came out with their tensor unit, their TPU, and that's an interesting design point that's putting pressure on the GPU to do things that are custom. NVIDIA went after that whole hog. AMD did not. How does that shape the future? Does it make the GPU less attractive? And for HPC, I think it has, trying to be satisfy the needs of multiple masters, you're going to have compromises. So how do you do that flexibly? That would be great if I could basically configure my GPU to do any precision at any point in time and still get the kind of performance that I would get from the highest end system. I think it's going to precision and data formats and functional units to support those in a way that's dynamic and flexible is really going to be an interesting path forward. So I really like that question. Okay. Perry asks, clarifying question. In these embedded systems, often CPU and GPU have shared main memory. Yes, they do, right? That opens up other considerations. Obviously, the memory reference pattern for something that runs on the CPU and the GPU are going to be very different. How do we adapt for both of those? How do we find the right management of that? Well, we need to do a lot of simulation. We need to do a lot of evaluation. I think the key, and I'll throw this back at you, Perry, what are those applications that are running? What is going to be the most promising applications to leverage that more of an APU class of system? AMD came out with their APUs, and I'll say they were marginally successful. I think the Tegra approach is probably a better target for a lot of things that are, Tegra and Xavier. There's some really nice features there. I think the edge computing is going to be a major player, and GPUs are going to play a huge role there. So it does open up a lot of considerations. And then how do I build clusters of these SoCs? That's interesting as well. So, I think these are all good targets for future research. Alan Kruth asks, can you comment about the possibility of in-memory computing in GPUs? I think we're already seeing some of that being done. I think the basically pinning things closer to memory, or making memory more manageable, but basically doing the computing in memory. I think it will come. We've tried this before because of the differences in DRAM technology of the day and the standard CMOS processes for random logic. They just weren't compatible to be viable. But I think we'll see that, we'll see processors in memory again. So, and I think as you start to see programmable fabrics where the memory system, the particularly non-volatile memory, is on on the same network as the L2 cache, that's interesting. You're going to start to see some very interesting configurations coming out from different vendors. So I think there's a lot of work to be done in terms of particularly new memory systems for GPUs, as well as in-memory computing. Samdip asks, I have a slightly non-technical question. If someone wants to collaborate and research with you and your group, then what is the best way to reach out so that we don't end up in spam folder? Well, you can always, if it's me in particular, an email is pretty much all you need to do. But again, that's, generally, I would encourage you to, and your advisor to just send me a note. We're pretty open to collaboration. If there's again, you should figure out what it is you would like to collaborate on and how you want to contribute. We're always open. I collaborate with a large international community, and it's what makes my job a lot more fun. Okay. I've answered all that have been posted. Any other questions? So I want to thank everybody for, again, joining this class. I think we had some great discussion. I did see a lot of good questions coming out, and you're spot on with many of your questions. Just shows the level of knowledge and expertise in the HiPEAC community. It's very impressive, and I'm proud to say I'm a HiPEAC member as well. So with that, I think I'll leave you to I know we're at the end of the HiPEAC classes, and this is, so I want to thank the organizers, Koen de Bocher, and the rest of the organizers who really made this very easy for me, and also to the students in the classes. I also want to recognize my own students. Without those students, I would really have a tough time presenting all of this work. So with that, thank you very much, and have a good rest of your day, evening. Take care.